You place a glass on the table. You reach for it, switch on a lamp, and light crosses the room almost instantly. Everything seems obvious. The table is here, the glass is there, and objects have definite properties whether we watch them or not. At everyday scales, this picture works remarkably well. But make everything smaller, smaller than dust, smaller than molecules. Eventually, you reach atoms, electrons, and photons, and the rules your intuition depends on begin to fail. The strange part is that this microscopic world isn't somewhere distant. It is inside the glass, the table, the lamp, and even your own body. So what is reality actually like when we stop relying on the assumptions our senses gave us? Take an electron. You might naturally imagine it as a tiny object with a definite location, whether we know that location or not. But quantum mechanics forces us to be more careful. And this is where popular explanations often go wrong. Quantum mechanics does not simply say that electrons are tiny balls behaving bizarrely. It does not say that anything can happen. And it does not prove that human consciousness creates reality just by looking at it. What quantum theory actually provides is a mathematical framework for predicting the probabilities of different measurement outcomes. That distinction matters. In classical physics, uncertainty often means that a definite answer already exists, we simply don't know it. A coin hidden under your hand is already heads or tails. Quantum theory is deeper. Its mathematical description contains relationships between possible outcomes that cannot simply be replaced by a classical list of hidden properties without producing experimentally testable differences. And physicists have tested those predictions repeatedly. So at the quantum level, questions like, where is the object, or what property does it already have, can become incomplete unless we also specify what is being measured. This is the conceptual wall. Our mistake may not be that nature is behaving strangely. Our mistake may be assuming that our everyday idea of normal was ever deep enough to describe nature at all. And we need to separate this from the mythology surrounding quantum mechanics. You've probably heard claims like, your thoughts create reality. Everything is vibration. Quantum physics proves consciousness controls the universe. These statements use scientific vocabulary, but vocabulary is not evidence. When a detector interacts with a quantum system, a physical interaction occurs. Energy can be transferred, information can become correlated with the measuring apparatus, and the system can interact with its environment. None of this requires a human mind to stare at the experiment. The word observer causes enormous confusion. In physics, the important question is not necessarily whether a conscious person is watching. It is what physical interaction occurred, what quantity was measured, and what outcome the theory predicts. The real quantum world is already strange enough. It does not need mystical decoration. So let's forget the internet version and start with an experiment. Imagine a barrier with two narrow openings and a screen behind it. Send ordinary particles through the openings, and you would expect two groups on the screen, one from each opening. But under quantum conditions, something different happens. An interference pattern appears, bright regions where possibilities reinforce one another, and dark regions where they cancel. And remarkably, even when particles are sent through individually, the accumulated detections can build this same pattern. The better description is not a tiny billiard ball mysteriously splitting itself in two. Quantum mechanics assigns probability amplitudes to possible alternatives. These amplitudes combine. Where they reinforce, detection becomes more likely. Where they cancel, detection becomes less likely. Mathematically, the probability is related to the squared magnitude of the resulting amplitude. Probability is proportional to the absolute value of amplitude squared. That small mathematical difference has enormous physical consequences. It is also why saying, the particle goes through both slits can be misleading. It makes us imagine a tiny classical object physically dividing itself into pieces. That is not what the mathematics requires. Instead, the quantum state provides the structure from which measurement probabilities are calculated. And now the chain becomes clear. The double-slit experiment reveals interference. Interference requires amplitudes, rather than ordinary classical probabilities. Amplitudes make superposition meaningful. Measurement interactions can destroy the coherence required for interference. Quantum states produce structural uncertainty. The same framework explains discrete atomic energy levels and, through quantum electrodynamics, the interaction of light and charged matter with extraordinary precision. These are not random collections of bizarre facts. Each result pushes us toward the next part of the theory. The biggest mistake is taking all of this and translating it immediately back into the comfortable language of classical objects. When people hear electron, they often imagine a tiny marble moving along a definite path. That intuition is useful for everyday objects. It lets us predict where a ball will land or where a planet will be in its orbit. But why assume that picture remains valid all the way down to atoms? We ask, where is the particle really? Which slit did it secretly pass through? What path did it actually take? Those questions assume that the quantum system possesses a complete collection of classical properties waiting to be discovered. Quantum mechanics does not require that assumption. Instead, we begin with the quantum state, use it to calculate probabilities, perform the experiment, and compare nature with the prediction. Science is not obligated to provide the picture our imagination prefers. Human intuition was trained by interacting with tables, rocks, tools, falling objects, and other large-scale things. At that scale, quantum effects usually average out and classical behavior emerges. So when we descend to atoms and electrons, our brains bring the wrong visual toolkit with them. It's not your fault that quantum mechanics feels wrong. Your intuition was trained on the wrong scale. You don't need to become less logical to understand quantum mechanics. You need to become more careful about which assumptions you carry into the experiment. Quantum mechanics does not say nature has no rules. It says the rules are not the classical rules we expected. Uncertainty does not mean anything goes. Probability does not mean there is no structure. And randomness in individual outcomes can still produce astonishingly precise patterns across many trials. The strange part of quantum mechanics is not that reality stopped obeying rules. It is that reality appears to obey rules we never could have invented from everyday experience alone. So what should you actually remember? The next time someone says, "Quantum physics proves," pause and ask 5 questions. First, what experiment produced the claim? Second, what quantity was actually measured? Position, momentum, energy, polarization, spin, or a correlation? Third, what did the mathematics predict, and what interpretation was added afterward? Fourth, is a classical analogy being pushed too far? And fifth, what evidence could prove the claim wrong? These questions remove an enormous amount of vague language. Quantum mechanics is not valuable because it lets us believe anything we want. It is valuable because it doesn't. The theory is constrained by mathematics, tested against experiments, and forced to make predictions that nature can confirm or reject. And that may be the most important lesson of all. When reality disagrees with your intuition, don't change reality to protect your intuition. Change your intuition